can do it. So objective of these lectures to introduce the stiffness methods to analyze the truss and the stiffness method that can be applied for both determinant and indeterminate structures. If you need more information, you can read it from these books. I think this books is available in our library. If you just search on the Latrobe Library Structure Analysis, and it will be available online. You can read it online, or you can you can do it easily. You can read it online. You don't need to purchase it and so on. But if you attend the lectures, these ones, you should be okay to take anything that you require for to complete the assignments. Now stiffness methods. Truss. First of all, we have some students from telecommunications and electronics. Probably they will not know what is truss and what would be the usefuls of that truss. Now the truss, you have seen the bridge, like you have a river bridge. You might see in the river bridge. In the river bridge, you might have some kind of these kind of a patterns that you've seen. So that is a kind of a structural members in civil engineering. We call it that is called truss. That is the system called truss. The main philosophy of the truss that it truss has all the joints that we have. The loads are only applied to the joints. You can see the loads, and you will never get these ones. You will never ever get these ones. No, that is wrong. The truss will not get any load coming on to the members, right? So that is green one is wrong. They will not have any. So the only the beauty of this truss, the loads are only acting at the joints, which is a good part. That is the one philosophy. Another ones that I would suggest that these joints are made of the some kind of a plates. Let's say I will just zoom in for this part here. So if I have this member here, these members here, they let's say connected with some kind of an bolt. Good. All right. So where we are? Yeah. OK, so let's say we zoom in on this, and then you have a plate. These members. So if I apply the load here, these moments or the bending will not going to transfer from one member to another member. So I hope you can understand. So if I bend another one, there is no direct, like if you have welding, like if I weld directly on this one, if I rotate this one, they will rotate. But this is a plate, and that's plate separating them. So therefore they are in the separate zone. So they will not be of bend. If the one member bend, the another members will not bend. So that's the truss. I hope you understand this one. So we want to calculate the deflections, like if someone apply the load, how much this point B going to go in X direction, how much point B going to go in the Y direction. That's what we want to find. We want to find how much these are applied in these members. Internal force meaning that is an internal strength. Internal strength meaning, let's say there are two students holding my two hands, and they are trying to pull my two hands. I hope you understand. My hands are like I'm just expanding my hand. Student X is holding me, and he's pulling that left hand, right, and he's pulling towards the left side. And there is another student, Y students, he's pulling my right hand. Now I have my internal strength. Internal strength meaning I'm very uncomfortable situation if someone pulling me from two ends. So I have my own strength, internal strength, to not let me pull. Right, I'm holding those two guys very tightly. If I'm very strong, that is my internal strength. Similarly, those guy has his internal strength, internal resistance to for the external forces. So that's we want to find it out. How much internal? Someone, let's say X students going into the gym, and he is following a lot of food diets and all. He's very healthy. It has a lot of internal energy. He can carry 40 kilograms and can run 1 or 2 kilometers. There are other students, he's not going to a gym, not so much strong. So the internal energy for that X student is more than another Y students who might not be going. So that's internal. So in the truss, you will come across two questions. Or maybe three questions. One is what is the displacements? Any particular joint, what would be the displacement of that particular joint, what would be the internal forces in the each members that you're going to experience. And another one, what would be the reaction force at the supports? Every members, they are not in the space, right? Everything are sitting nicely somewhere. So it is supported. So when you apply the external load, how much reactions it will create? That's typically three things that we need to investigate using the stiffness methods. I'm with you. Don't worry. Once you attend these lectures, I'm pretty sure regardless of your disciplines, you can crack it. You can crack it meanings you can solve any questions, I will guarantee you. So the stiffness methods are widely used in commercial structure analysis softwares like Abacus, SpaceCAE, ANSYS. There are around 500 softwares available in the markets. And those software, I don't want to teach you any particular software where you can just sit down and you press some buttons and you get the results. No. How does these softwares are performing the calculations? That is the overall objective of these subjects. We want to go behind the screen and see how these softwares are running. I will show you one of the software which is SpaceCAE that will going to that we're going to run it probably next week, not this week. So what is this is I think last week I explained you what is this overall method is about. Let's say if I give you rectangle and let's say rectangle has a width B, a depth D, and if I ask you to calculate the area of this rectangle, you said, I'm an engineer, regardless manufacturing, civil, electronics, telecommunications, you are in the position to calculate area equal to B times D. Simple. That I know this one from my undergraduate degree. If I don't know, let's assume that I give you this information that area equal to width times depth. That's how you can calculate the area. But if someone give you this area and say that please calculate the area, you will stretch your hands. It is not a standard shape. It is not a standard shape, meaning it is not a square. It is not a triangle. It is not a circle. It is not a rectangle. We have a pretty well defined equations to calculate the area for those standard shape. This is not a standard shape, and therefore I can't calculate the area for this standard shape. Yes, I agree with you. As an engineer, you can't calculate the area for this one. What we do that we can divide this whole shape into known area, like you can divide them into squares. And if you know the area of this one square, and then if you just add them all the squares, you probably estimate the total area for this one. Some students might think, you are not giving us the correct information because you are not considering this area. Of course, I agree with you. This is an approximate. This method, whole methods will not going to give you the answers spot on. It is an approximate. I can repeat. This is approximates, and we are engineers. We don't want like a 1 to 500,000 millimeters accurate answers. No, within few millimeters here and there, we are okay. We are not. What can I say? We are not so much picky about very fine details. That's what we want to have estimated. So the final, the mass you will get, the final, the details you will get. So the overall objective of these methods that when you come across with the very complex, we will divide them into the very small elements and then we will work it out each element. So if someone give you this whole truss, what we do, we break down into the various elements. We break down, let's say like this, right? And we work on this one. We work on this one, we work on this one, we work on this one, we work on this one individually, and we combine them together, right? We will add them together, we minus them together, we multiply together, we will do something. But what we do, we work on this one first, forget about everything else. Then we forget about this one, everything, we work on these ones and so on. We continue that philosophies, right? So that's what the overall objective of this one. Now, there are a few terminology that I like to give you, that there are pin supports. Pin meaning that if you hold your point, pin meaning like this. So if you hold this point with the pin, let's say right on pin support, what does it mean? Saying that you can, if I hold these ones with my hand, I can rotate these points freely. but this point cannot go in the left direction, cannot go in the right direction, cannot go vertically, cannot go down. Right? This is restricted because it's pin like a door. If you have seen the door, you can open the door, close. You can close and open the door freely, which is a pin hinge there, but you cannot take the door out and you cannot move that door left, right, or up and down. Right? If you do that once, your mother, fathers will gonna kill you because that might be damaging the door. Well, you can open the door and close, right? So that's that kind of things. Now here we have a roller. So roller meaning like a skateboard. You still have this point. I'm talking only on the point. OK, so if I these points can go left to right, but it cannot go up and down. Right. So that's kind of a roller situations there. So roller supports that. Now, so that's pretty clear. Now, first thing first, I need to provide the elements. So this in the vocabulary, it is called elements. So the number with the square, I will tell is element number 1. Number with the square, another one is an element number 2. Number with the square is element number 3. Number with the square, element number 4. Number with the square, element number 2. So to have total 5 elements. And how do I represent it? When I see the number with the square outside, it is called element numbering. Element numbering is arbitrary. There is no rules. You can put 1 here, no problem. You can put 2 here, no problems. Or you can put 3 here, no problem. There is no any rules that you need to start with any particular 1, any particular 2. There is no rules. There is no, then your answer will not affect it. Everyone will get the same answers if you use different 1, 2, 3, 4. So the someone will say, what is the reason for it? It is just the format that we want to we want to know how many elements there, so we can work individual elements. So therefore we give them numbers, right? But it does not matter which formats that you're going to follow. It's a user defined. Then you have a location vectors. So you will see the arrow. And again, this location vector does not require, it's user defined. You can put this way or you can put this way. Now this is a location vectors. Every element has these square and numbers, and they have a location vectors. Now what is this location vectors meaning? Location vectors will identify the near node and far node. So if I see this arrow going from left to right, so this node is called near node and this node is called far nodes. Now I'm putting one more vocabulary that this is element. Each element has a 2 nodes. 2 nodes meaning the point and point is called node. Node is a end of elements, left and right end, the far end of the elements when they finish. So that is called node. This is also called node. This is called element. And if I put the arrow left to right, meaning this one is near node, this one is far node. OK, that's how we identify. This arrow meaning this is near node. This is far node. This arrow for this element number 5, this is near node, this is far node. For this arrow is telling me that this is far node. For element number 3, this is near node. So I hope it is made clear. So I make it two things clear. Square in the numbers is representing the element number. Arrow location vectors representing the elements node, far and near node. You can identify that. And again, those both are user defined. You can put the way you like it and the answer will not going to change. For your assignment, for your final exam, any questions, we will give it to you. So you no need to worry about element 1, 2, 3, 4. To make it easy, we will give you those details because there is no logic. There is no engineering, because what is the engineering here? If I ask you, can you please put 1, 2, 3, 4, 5? There is no logic because it's arbitrary. It's user defined. What is the logic if I ask you to put the arrow on the location? There is no logic. There is just you just put it anywhere. So there is no engineering. So there is no any assessments. We will give you that details, but you need to know what is the meaning of those numbers and arrows and why are they going to use. So therefore, I'm giving you this information. All right. Anything else? Probably that's it. So node we cover, element we cover. Each member has two nodes. We covered that. All right. Another definitions now I like to give you is called degree of freedom. Now, what is degree of freedom? Again, you don't need to remember anything. You don't need to remember anything, meaning we will not going to ask you what is the definition of degree of freedoms. You don't need to remember anything in these subjects. You can practice it, but you don't need to remember any definitions. You don't need to remember any equations. You don't need to remember anything. You just need to understand. You need to apply it. You need to be engineers. We will not gonna make you engineers, which you need to remember anything and panic. No, you don't need to remember anything. Just practice it. Just follow the instructions, and you need to know how to apply it. So degree of freedom. What is degree of freedoms? Now degree of freedom. So let's say you have an element number 1. Now this element at each node has, let's say at this left side of the node at node number 1, it has 2 degree of freedoms. It can go in the X direction and it can go in the Y directions. So each element has a 4 degree of freedom. Do you agree with me? Because it has 2 nodes and each node has a 2 degree of freedom. It can go left and right. It can go in the one left and right, and it can go up and down. Similarly, you have here, let's say 3 and 4 is X is a 3, Y is 4. So that node here sitting can go in the left, right, and can go up and down. So each element has a 4 degree of freedoms, as you can see here, or each node has a 2 degree of freedoms. You can put that way, that each node has a 2 degree of freedom. How many nodes you have? Node number 1, node number 2, node number 3, node number 4. So there are 4 nodes. So total degree of freedoms here is 8 total degree of freedoms. Everyone agree with me? It's just, what is degree of freedom? It is a possibility of the displacement of the whole systems. How much possible displacements are there going in X, Y, X, Y, X, Y. So each node can go in the X, Y direction. Therefore, it has a 8 total degree of freedoms. It is basically how many node times by 2. And I forget to tell you that number with the circle, it is representing node number. Number with circles representing the node number. So node number 1, node number 2, node number 3, and node number 4. Right, so that is the another vocabulary which I'm giving you. Node number 1 with circles, it's called node numbering. OK, and again, there is no rules which numbers goes where. You can put arbitrarily. You can put wherever you feel 1, 2, 3, 4. OK, there is no rules for it. Right, so I explain you what is the number in the square. I explain you the vectors. I explain you the numbers. I explained you total degree of freedom so far. Now, there is another ones that I like to explain you that call fixed degree of freedoms. Now we have total 8 degree of freedoms. Now out of 8, total 8 degree of freedoms. Out of 8, we need to find out how many free degree of freedoms. How many free degree of freedoms? Free degree of freedom. So look at these ones. So this node here, node number 2, there is no any supports. So this node can go in this direction, can go in this direction. So there are 2 free degree of freedom for here. Do you agree with me? Because if you take this node number 2, there is no support, so they can. All right, so there are 2 free degree of freedoms here for these nodes. If I take these nodes, then you have another 2 free degree of freedoms, right? For node number 3, you can see this node can move left and right and it can go up and down. Now, if I come back here, because let's say another 2 free degree of freedoms. If you come back here, then this point is pinned. It cannot go left to right. It cannot go up and down. So there are 2 fixed degree of freedoms. Do you with me? This is a roller. You can see there is a roller. So the roller cannot prevent this direction, but this point cannot go in this direction. So there is a 1 fixed degree of freedom here. And there is a 1 free degree of freedom here, right? For roller. So How many free degree of freedoms? 2, 4, 5. Total 5 free degree of freedoms. You with me? And 2 and 1, total 3 fixed degree of freedoms. Total 3 fixed degree of freedoms. Right? So therefore, we have 5 free degree of freedoms, 3 fixed degree of freedoms. OK, so you with me, right? Total 8. And out of 8, 5 are free degree of freedoms and 3 are fixed degree of freedoms. And fixed degree of freedoms are known degree of freedoms, which are 0, and free degree of freedoms are unknown, which we need to find. Now, I hope you understand that. Now the story that this arrow representing that are numbers, so there's are the degree of freedoms. As I mentioned, total 8 degree of freedom. So therefore, you have total 8 numbers there. Now, your lowest number. So this numbering is important now. All others before are not logic. You can put arbitrarily whatever you like it. But these ones, you need to put it with the logic. So you need to start with the free degree of freedoms. So 1 and 2, right? Because it is free. 3 and 4, because it is free. So the lowest number of degree of freedoms, the numbers that are goes 1, 2, 3, 4, the starting point 1, 2, 3, 4, you need to put it with the free. Of course, you can put 1 and 2 here. Of course, you can put 1 and 2 here because both are free. There is no any issue. You can put 3 and 4 here. There is no issue. But of course, all the smallest degree of freedoms, you need to put it with the free degree of freedom. So total 5 free. So therefore, I put 1, 2, 3, 4, and 5 free. They are 5 free. And then you start with fixed 6, 7, and 8. So there are highest numbers are 7. OK, so I hope you understand that. I explain you everything. The number in the square brackets, I explain you the arrow, I explain you the fixed degree of freedom, free degree of freedoms, and everything. Now, these figures here, students, tell me what is the total degree of freedoms here? Work it out. OK, so here you have said the total 10. So probably this one is a free, 2 free degree of freedoms. Here 2 free. This one is 2 fix because pin. This one looks 2 fix. And this one 1 roller. So 1 free and 1 fix. So 2 free, 4, 5 free, and 5 fix. Do you agree? Or right? So I can put 1 and 2 here, 3 and 4 here. Probably the 5th one is going here, 5, and then 6 is a fix. 7 is fixed, 8 is fixed, 9 is fixed, 10 is fixed. Right? All right. This is all good so far. OK, now let's move on to the next one. Now, when you have these trust systems, you have two kind of systems, which is a global systems. Global systems meaning that whole trust systems have a whole like a coordinate system XY, where somewhere you have origin 0, 0. Based on that 0, 0, you have these coordinates. You can say what is the coordinates here. I'm not sure, 4, x, 3, and something like that. Let's say 8 and 3, and let's say 8 and 0 or something like that. So you can have a 0, 0 somewhere. And then with the 0, 0, you have all the coordinate systems are sitting, all the nodes has their coordinate based on that 0, 0. So that is your 0, 0 systems. That is called global systems. And you have a local systems. Local systems meaning that each member has its own systems. So that let's say going from their members from here, and it has this one. So it's represented by let's say y dash and x dash. So these guys, one has his own systems. This number 4 has let's say this is x and this is y dash. These guys 5 has his own local systems. Let's say X dash Y dash. This guy has his own systems, local system X dash and Y dash. You understand what I'm trying to say? So there are two systems that I just want to identify X and Y just without this prime. It is a global systems and it has a all the element has its own local systems and we need to talk with each other because it's like a federal government and state government. Let's say this is federal government, your country government, and this is your state level government. So yeah, they need to talk with each other. They can't just go opposite to each other. So we will make them to talk. OK, and local systems, because when you're going to work with these ones, we're going to work with local systems. And then when we work with the whole systems, we're going to work with the global system. So therefore, we need to make a relationship between the local and global systems. That's I'm going to do it next. I'm making very simple so everyone can understand. Students who are electronics and telecommunication who might not have background, probably still they can be able to absorb all these informations that we are putting it here. But unmute yourself if you don't understand any of these ones. Now let's take a one elements. Let's take a one elements meaning let's take this guy. Any. Just an example, just get that one out because as I mentioned, this is stiffness methods. We are not going to work with the whole systems. Do you remember these examples which I give it to you that you can just create it and let's work out only one area, this one. And then once you work out one, then you can do it for everything. So let's grab only one element. Let's take one anything. Now, if I have one element, let's say one element and let's say I fix or I hold it here with my hand and someone just pushing that once from one end. You understand what I'm saying? That is a one bar. You hold one end and someone just said squeeze it, right? So when you squeeze it, what gonna happen? That this bar gonna deform at a some let's say symbol DN. Deform meaning it gonna be smaller, right? Because nothing is strong. If you push something and if you hold other end, it will be deformed. So let's say that deformation is dm. You with me? And how much you are pushing with your hand? Let's say q and dash. That is the force that I'm representing. And that is a local system, by the way. This x dash and y dash has a local systems that is putting here. And you are deforming at a distance dn, right? Distance dn. And you are applying the force here and you are holding it with your hand here. Now, then it will create the reaction force, right? Because your element is not in the space. It is at one place, meaning that all this force is going from this side. There is an equal and opposite force that is trying to be in equilibrium. Therefore, your bar is sitting at one place. You have a home. Your home is not moving. It is at one place because it's in equilibrium. It is not in the space. It's not an aeroplane. It is not a skateboard, right? So any structural elements, any truss members, they are in equilibrium. Equilibrium meaning that if you push something, that will be holding by some other persons or someone that is also pushing from the other end, virtually equal and opposite. That's how it is balanced. So that is the force that QF that is sitting here. Now, what is the logic for this end? And you remember that near node and far node. Every node has a definition. Every node has a definition, meaning it can be classified as a near node and far node. Who gonna tell? This guy gonna tell us. Let's say there is a location vectors. That arrow is telling me that the tail side is a near node and the head side is a far node. So that is the QN and QF. Right, so I hope you understand that. Now, what is the logic behind this one? That is the relationship between the force and displacements. How much force you are applying equal to some constant and you have some deformations, right? So this is force equal to some constant value times by the distance. So that is a relationship between force. If I'm applying that much force, I'm getting that much deformation. If I apply more force, I'm getting more deformation. It's a linear relationship with some constants. Now, how do we get this relationship? Let me explain you that. Electronics and telecommunication students, just listen it very carefully here. So if you have a stress, If you have a stress, then you can define force over area. Right, and this one force is here, Q and S, and area is, let's say, area. I hope it is clear so far. Stress is equal to, let's say, Young modulus. Let me write it in another way. Young modulus, which is the material property, how strong the material is, how steep the material is, that is called represented by Young modulus, is equal to stress over strain. That is the definition. So if you take the ratio of stress over strain, again, you don't need to remember these equations. We're not going to ask you in the exams that prove these ones. No, you don't need to remember anything. It's just the logic. I want to make it familiar with all these one. So if I want to calculate the stress, which I can substitute here. So stress is equal to Young modulus times by strain. And the strain is change in length. How much length is changing over original length. So stress is equal to Young modulus. How much length is changing? Dn. Let's say original length is capital L. Right, so I can substitute this value here, E times dn over L. Now I need to find this Qn. Qn dash is equal to AE over L, because A multiplied by E over L times by dn. That's what I got it here. Look at that. Right. So that is just the proof that this is the force times displacements. Area, how much cross sections area that you get it. It is rectangular, square, circular, you can find it. Young modulus, how the materials, what materials is made. If it is steel, concrete, or aluminium, what materials is made. It has a Young modulus value based on its stiffness, how stiff it is. If you force applied on that one, it is deformed very easily, or is it not deformed very easily. That is the Q definition. If the higher the Q, higher it is difficult to deform. That's what it's representing. Now, so this is the relationship. So if I apply the force here, that much deformations I will get. Similarly, I will get opposite, exactly opposite, but it's a minus sign. So you can say exactly the same. It is just a minus sign. Similarly, I will hold this end. I will hold this end and I will pull this end. And same thing. Q and S, just definitions. And if I pull minus AE and deformations, now this DF, because the far end is pulling. Similarly, you have reaction force at the other end. So I hope you understand this story. And if I superpositions, meaning that if I superpose these guys, I will get this. I will superpose these ones, I will get this. So similarly, I can superpose force at the near node, AEDN minus this. And QF, I can add them together, superpose. And then if you know the two equations, then I can write it in the matrix form. Force AE over L common, 1 minus 1, 1 minus 1 minus 1, 1 dn. So this one is called stiffness matrix. This one, force displacement relation, Q equal to stiffness times D. So you have a stiffness matrix. OK, again, you don't need to remember that. Just keep it that relationship, Q equal to KD. And by the way, this is the local systems. We take only one bar and we develop the relationship between the force and the distance in the local systems, right? Q equal to KD. I hope it is clear. Now let's do the transformations of the displacement from global to locals, because as I mentioned, we have a relationship before, Q equal to KD, right? That is force in the local, force in the local, displacement in the local, and stiffness matrix in the local systems. Now, these displacements which you can see, we can transport it into the global, right? Because this displacement that you see here, which is local, that one bar is this one, but we want to make a relationship between local and this one. So let's have a relationship between the displacements. So if you know the local displacements, you can get the global displacements, or you can, if you know the global displacements, you can calculate the local displacements using this relationship here. So what happens here? We take the same bar, and if I move that bar by, let's say, some distance. Let's say I move this bar by dn, then the relationship, the same dn, by the way, same dn, displacement dn. So this dn, then if you have, let's say, this will have a degree of freedoms here, and if you want to get the two component, let's say I move this dn this direction, and if I want to get the x component, y component, and if you use the trigonometry theta x and theta y, you will get the deformations dn. And by the way, this is the global, global, right? This is global systems. This is global systems, and this is local systems. This is locals. I should use the different colors. This is a local, and this red one is the global. So that's we develop this one using the trigonometry. Again, you don't need to go in the great details of how we get this one. So of course, you can figure it out yourself if you want, but it's not too much complicated. It's just a trigonometry that we done. The important part is this is a relationship of near node displacements in respect to the global systems. Similarly, far nodes, you can do this far nodes one. You can just displace in the two different approach, and you will get the far nodes. And based on that ones, you can just write the matrix dn over df. By the way, cos theta x we just replace by lambda x, cos theta y we replace by lambda y, and so on. So you have another relationship. That is displacements. Now, what about the force that we are applying? So I think that is D equal to TD. And I think similarly, you can do this one as well. D equal to T transform small d, right? T transforms. I think last week we explained that one's T inverse. So you can just go through this ones. It's not super complicated. Again, dn same bar theta x theta y, and we get the relationship between these global and locals. What about forces? Same thing. If you are applying the force in the global, local, cos theta x, global, cos theta y. It's just a trigonometry. The force and so on. This is global. Capital Q is a global, and small q is a local. Okay, and again trigonometry, and you can get the matrix, and you have these equations, which is the global force and local force. Now, what would be the relationship? Q equal to KD. I hope you know the first relationship that we develop. Q equal to KD, which is the local, and we want to get the so Q equal to KD. We can substitute D equal to TD, which is the local displacements, and that's we done it here, local to global. We substitute K equal to KTD, and we multiply T transform on the both side. So these whole things that you can see, that will be your stiffness equal to T. So I substitute T transform here. I can substitute small k here. I substitute the small t, and if you multiply, this is important. This is the matrix that we just going to use. That is the matrix for this elements. OK, for each elements, that is the matrix that we're going to use, and that is the global matrix. You can see this is the global matrix for these ones. Now, the beauty of this matrix, you don't need to remember this matrix again. We will give you this matrix in your assignments in the exams. You don't need to remember that. So that is clear. All the diagonal will be positive always. So that is a stop sign when you do the calculations. And if you screwed up something, and if you're getting the negative answer along the diagonals, go back and check. One stop sign. Second stop sign. This line, this 3, 1, whatever you got here, you will get same here. Very nice. So if you work out those 3, and if you work out those 3, and if you get the different answer, go back and check. Similarly, this guy, these guys, and these guys, exactly the same. And these guys and these guys, exactly the same. All are stop signs, making sure that you will make sure that you check back. Another one, there are plenty of opportunities that will not be able to go wrong. This guy, same as this guy. Look at that. These guys, same as these guys. Look at that. right? So there are plenty of way we're going to make it check. OK, so hopefully we will do one examples and then it will solve. Now, this is an examples. After completing these examples, once I show you these examples, every student in the position to assignment 1, question 1, part A. I can repeat again. Question 1, part A. Every students in the position, once I show it to you, every position should be able to do the part A. If you are follow 6 when you are near to the assignments, it will be very likely that you're going to be able to assemble everything together. So if you want to finish your assignment smoothly, not overloading yourself and panicking at the very end of your assignment, please do the part A this week. It will take you half an hour, 1 hour, 2 hours, depending on your capacities. OK. So that's I will show you at the end as well. What are the questions, typical questions look like? So determining the stiffness metric for each member and assemble the matrix to find the global stiffness matrix. That's the questions. And this is the truss systems given to us and we model it. This is given to you again. So this is the questions, by the way. And then this is the steps that we need to follow. Like it has a global systems given to you here. That is the global systems XY. You can see that is 0, 0 here. That is given to you. Then you have given this 1 and 2, which is your element numbering. Number within the square is element numbering. OK, very nice. It give you location vectors to represent 1, 2, and so on. And location vector given to you. Number within the circle, 1 and circles, it is your node numbering. Number within the circle, node numbering. Number within the circle, node number. It is given to you, node numbers. It is also given to you your degree of freedoms. There are total 6 degree of freedoms. 1 and 2 look like a free degree of freedoms. 3 and 4, which is fixed degree of freedoms. 5 and 6 are fixed degree of freedoms. I hope you understand this everything, right? Unmute yourself and saying that in the chat, saying that I don't know how you go from here to here or any numbers. Oh, this is, by the way, 2 kilonewton is a force applied on this ones, and this is pin and this is pin here. And length 3 meters, 4 meters. That's the length of this truss. So unmute yourself, put it in the chat saying that I did not understand this letter, this number, this arrow, these numbers. How does it come in? I give you 30 seconds and so on. And tell me if you tell me if you don't understand the figures on the left and figures on the right. Any numbers on the figures on the right, you tell me that OK, this number, particular numbers going on here, these letters, what does it mean? I did not understand where you're gonna use it and what did you, the theory that you explained, you did. Now this point here, which is pin, meaning this point cannot go in the vertically, it cannot go up and down, it cannot go horizontal, it cannot go left and right. So this is called fixed degree of freedom. This point here, which is pin, which is supported. Now this point cannot go left, right, cannot go up and down. It is like a door, is a hinge. Which you take a hinge, this hinge will not gonna go left, right, it will not gonna go up and down. So this is fixed degree of freedom. And this point, which is free to go in the X, Y, or vertically, it can go, it is not supported. So this point has a 2 free degree of freedom. It has a free degree of freedoms. So these 3 and 4 are fixed degree of freedoms. Look at the left side. 5 and 6 are fixed degree of freedom. And 1 and 2 are free degree of freedoms. Ahmad Asif. I will come back to you, Syed. Ahmad Asif, what about you? Can you do the fixed and free degree of freedoms? You need to look at when you have supports, pin, it has 2 fixed degree of freedom. Roller, 1 fixed degree, one free degree of freedoms. If you have a point where no supports, it has free degree of freedoms. All right, now student said what is the number in the circle and what is the number in the square box. Okay, so let's start with the square box. Number in the square box, look at this. The whole truss system has a two elements. Two elements meaning this is element number 1 and element number 2. So the number in the square represent the element numbering. 1 and 2 represent how many elements you have, how many members you have. If you don't want to say how many, member number 1, member number 2. Arbitrarily, user defines, you can put 1 here, you can put 2 here, and so on. That is doesn't matter, but we just want to know how many members are there. Therefore, there is a number in the square representing element numbering 1 and 2. Number in the circle that representing the node numbering. So how many nodes are there? Each member has a 2 nodes. That is the end of the members or end of the element is called node. And those nodes, let's say you can put the number here 1, 2, and 3. So the number in the circle representing the node numbers, the joints at the ends of the elements. Again, those numbers 1, 2, 3, 4 arbitrarily. You can put 3 here, you can put 1 here, you can put 2 here. Your answer will not change. 1, 2, 3, 4 does not matter. 1 and 2 does not matter. Okay, so all these are arbitrarily user defined. But we need to define it. And once you made the definitions throughout the examples, we're not going to make the changes here. We will stick with that numbering. We will not in the middle. I changed my mind. I want to call this one. No, not allowed. Once you fix those numbering, it is stay there for you to work out. Okay, good. So far, so good. So everyone knows what is happening in the left side figures and what is happening on the right side figure. Left side figure is the questions. Right side figures is the one that is called modeling. That is, we're going to break it down to work out. Right side figures will be given to you. If you open your assignments, we will open the assignment, one of the sample questions that will be given to you as well. But again, I will say, but you need to know what those numbers are representing. All right, I'm turning my camera because I need to write on it because I don't like to just walk you through. I want to work as a student. Okay, I hope you can see my screens and we're gonna work it out with you. Now here we have 3 nodes. Node number 1, node number 2, node number 3. That numbers within that circles is node numbering. And you have 2 elements, element number 1, element number 2. It will be given to you that numbers. And you have 2 free degree of freedoms, which is here. That is free 1 and 2, which are free, and fixed degree of freedoms, which is 3, 4, 5, 6. Right. Any questions there? All right. Now, what we need to do it? Let's start with element number 1. You can start with element 2, but what makes our life easy? Just say element number 1. Right? What we need element number 1? We go back to our lecture notes and get that magical equations. What is the magical equations I'm talking about? Come on, this one here. Edit, copy. Control V. Okay. All right. So this is the our matrix. Let me put it somewhere here so we can see it. Okay. Now we gonna represent this capital K1, which is representing the stiffness of element 1, equal to, we have, let's say, put area over length L. L is 3 meters. So L1, which is 3 meters. You can see that 3 meters given there. 3 meters. Now we need to calculate lambda x. What is the lambda x? I can explain you that. So before going to these ones, let me explain you that this is 0 and 0. And this one 3, 0. Do you understand these ones? Because your global coordinate systems are sitting here. Because you can see this arrow X and Y. So here you have 0, 0. meaning that you need to go along the x. If I want to come back here at this point, your x direction is 3, y direction is 0. So you happy for me to put the coordinate 3, 0 here. You also happy for me to put the coordinate here, which is 3 across, which is horizontals, and 4 above y. So you happy for me to put the coordinates 3, 4. You unmute yourself or put it in the chat saying that how do you put 0, 0, how do you put 3, 0 and 3, 4. That is based on this length given here. Starting point 0, 0 given in our figures because that is your global coordinate system x, y. And from that 0, 0, we done 3, 0 because x is 3, y is 0. And along this node number 1, we have 3, 4. X and y. So x first and y second. X first and y seconds. That's correct. I can explain you. So 0, 0, you understand. You have, this is x, this is y. So you have x and y. So how much x? If I have a 0, 0, if I want to go this point, I need to go across by 3, but I don't need to go anything on the y. If I want to come these ones, I need to go across by 3 and then go up by 4. So therefore we put 3 and 4, right? So that is the positions, the coordinates, x and so the equation for lambda x equal to, let me draw up these elements for you. So let me draw these elements. Let's say this is 1. Node number 1. That is node number 1 or node number 2. Sorry. Node number 2, which I draw it here. And node number 3, which I put it here. This node number 2, node number 3. I can put 1, 2, because you have 1, 2, and 3 and 4. So I can put 3 and 4. I can put the coordinate 0, 0 and 3, 0. Right? And the length of this one is 3 meters. Right? What I done? I just redrawed this. This guy here, 2, 2, 3, 3, 1, 2, 1, 2, 3, 4, 3, 4. Exactly the same. There is nothing I done. Just the new thing is 0, 0 and 3, 0. So this one I can put in the arrow. These ones location vectors. Let me put the location vectors here. Okay. Now here I can put this one x1, y1, or let's put this near node, far nodes. Okay, because we already know that. So this is near node and far nodes based on this arrow. This tail of the arrow representing this is number 2 is near node and far node. So this one I can say that x near, y near. And I can say this x far node, y far nodes. Do you understand that? Right? This arrow is given in our figures. And based on that arrow, I can put that is a near node and this is far nodes. And I can put this 0, 0 is x n, y n, because x near node, y coordinate of near node, x coordinate of far nodes, y coordinate of the far nodes. So far, so good. Okay, I'm just observing the chat. Let me turn on this side here as well. Activity, so I can do. How do you put 3 and 4? We done it. This one. Put in the chats. I'm observing on the other computers as well. So lambda x. Lambda x equation again. No need to remember that. Lambda x equation is xf minus xn over L. So xf and this is L. Xf is 3. Take away 0 because xf is 3. Xn is 0. Length is 3 equal to 3. Take away 3 is equal to 1. How do you put, sir, arrow directions are to be in X and Y, all good. Okay, there's no more questions. Lambda Y, I can put YF minus YN over L. So that would be 0. YF, YN is 0. Length 0 over 3 equal to 0. Right? So we calculate these all the values. Now we're going to substitute those values here. Let's say K1. This is K1, by the way. K1, that equation, whole equation is K1, this one. K1 equal to AE on L is 3. Lambda x square. So 1 square. 1 square is 1. Lambda x times lambda y. 1 times 0 is 0. Minus lambda y square. Please note this minus is not like minus 1 square. No, it is 1 minus and then 1 square. Okay, so making sure that you understand this minus which is outside. So it is 1 minus and then 1 square is 1. This one is 0. This one's 0 because lambda y is 0. Lambda y square 0. Lambda, this one 0 because lambda y is 0, 0. Lambda x square minus 1. This one 0 because lambda y is 0. This one 1. This one 0. 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 Okay. Stop here and I will tell you if how do I get what if we don't have a uniform CSA over the length. What is it? Uniform cross section. CSA meaning cross sections. See, cross section area. You will get always in uniform cross sections. Look, okay, let me explain you. It is very expensive to build the truss which has a non-uniform. If you are a structural engineer and someone will say that you have seen the truss, roof truss. Let me search. You always get the, but thanks for the questions. You always get these. I hope you have seen these kind of things. Now, if someone say that I have this cross section here and please reduce this cross section here. No, it is very expensive. Or let's say, look at these members. Look at these members that if you want someone to have this one, someone to have this one, and then another one having smaller. No. That's generally very unlikely happens. And then in that case, we can't use these methods. But I think you need to have a uniform cross sections throughout. Or if you have, again, you can do it. Let me give you for your questions. You can still do it, but very unlikely. OK, the question is that what about that I have different cross sections? I get your questions. Thank you. OK, now let's do this one. Thanks for the questions. Narayan. OK. All right. How about you? I agree with you. Let someone say that I have these members here. It has an area A1 and it has an area A2. No problems. What we do? We make element number 1. We make element number 2. We make element number 3 and we make one more node here. Does it work? And there is no issue. We can make it as many elements as you want. And therefore, that's the beauty of stiffness methods. You can break down your complexity at the local levels. So your figures become like this. Sorry. and so on. Does it make sense? What if we don't have uniform cross section, the Lancer? Yeah. Okay. Narayan. All good, Narayan? Got it. Thanks. Okay. Anything else? You tell me. I can't build this 100 100. Stop sign. I like this one. What do you mean? This diagonal. Positive. Very happy. Good. Second, this guy, meaning this guy, same as this one. Perfect. This guy, same as this one. Perfect. This guy, same as this one. Perfect. No issue. If something goes wrong, I will need to go back and check my calculations because there are a lot of multiplication and a lot of things happening. This guy here. Same as this one. Looks like it. Same. And similarly, this guy, same as this one. Oh, that's perfect. You can see that, right? Sorry, I'm making a lot of mess, but it's very important. So you may not be able to get wrong. If someone in my subject saying I'm failing the subjects and I can't submit the assignment on time, I will have a lot of questions in my mind that why students can't have this one. It's very simple. Another things I want to put it that you always put your x, y, x, y, x, y, x, y. What is x, y, x, y? First, you put the near node. So that is your near node. X, y. This is your far node. Always you put the near node. Always you put the far node. Always you put the near node and always you put the far nodes and x, y. So near node x is 1, 2. Far node x is 1 and 2. So I hope it makes sense. And we can just get these three inside. So AE, you get 0.33, 0 minus 0.33, 0, 0, 0, 0, 0, minus 0.33, 0, 0.33, 0, 0, 0, 0, 0. Some student might say that if I calculate this one, how about I copy this one? Well, you can if you are smart enough and if you are confident. Once I work it out this one, I copy here. Well, yes, possible. Once I work it out this one, I copy here. Yes, you can do it. Make sure you have good practice. Make sure you know what you're doing. Then you don't have option to go back and check. Okay. All right. So this is the first one done. Element number 2. We forget about element number 1. We just work out element number 2. And then element number 2. Let me draw this element number 2 for you. I will redraw these elements. 2 here. Let me get this element number 2 for you here so we can see it. Ooh, here. Got it. Thanks. Okay, there is last message. I'm just keep an eye on the chat as well. And paste. Okay. Okay, now element number 1 done. We will roll the element number 2. Element number 2, it has a 1 and 2, and it has a 5 and 6. It has this arrow going from here. So that would be your near node. This would be your far node. Then you have element number 2. What else you have? The length. I think this is Pythagoras theorem because this is 3 meters, 4 meters. So the length of these ones, if I want to calculate this length, 3 square plus 4 square. I think you know the Pythagoras theorem, right? Like this. If someone say that this is right angle, this is 3 meters, this is 4 meters. If I want to calculate this one, 3 square plus 4 square, which is 9 plus 16, which is square root 25, so which is 5. So the length is 5 meters. So length is 5 meters. Coordinate 0, 0. Here, this coordinate is 3, 4, right? So here, this is near node, so xn, yn. This is xf, far node, yf. Similarly, lambda x is equal to xf minus xn over L. Xf is 3, take away 0 over ln 5, 3 over 5, I think 0.6. 3 over 5.6. Lambda y, yf minus yn over L. Yf is 4 minus 0 over ln 5, 4 over 5.8. Right, let's get that matrix close to us so we know what is happening. All right, now let's say K2 is equal to AE on L, lambda x square, 0.6 square, meaning 0.36. Let me get my calculator close so I know what I'm doing. 0.6 square, 0.36, correct. Lambda x times lambda y, 0.6 times 0.8, 0.48, minus 0.36. Okay, this is not like minus 0.6 square. No, it is not positive. Okay, just be careful there. And minus 0.48. 0.48 lambda y square, 0.64, minus 0.48 and minus 0.64, minus x, so minus 0.36, minus lambda x lambda y, so minus 0.48, lambda x 0.36, lambda this one 0.48, minus 0.48, this one here, and minus 0.64 y square, which is 0.8, this one 0.48, and this one 0.64. Stop sign, check, all positive. These guys positives, one check done. I liked it. This one 0.36, 0.64, all diagonals are positive. First check done. Second check. This line, this guy same 0.48, 0.48, and this one same. Perfect. Quick check. These guys are same. Very good. Okay. This one here same. Perfect. No issue. Another check. These guys are same. Yep, looks like it. Perfect. And another check. That this one and this one same, and it is same. Okay, so I hope it is clear for you. How do we put it? First, we're gonna put the near node x. So near node x is 1 and 2. So near node x 1 and 2. Far node x 5 and 6. So far node x 5 and 6. So that first one is near node, second one is far node xy xy. Similarly here 1 2 5 6. Unmute yourself if you stuck somewhere. Questions? There is no questions coming up, so all good. Okay, so that's all good now. Now we can just multiply this one inside because we can substitute this length is 5. So AE and 0.36 divided by 5. That will give you 0.072 is just 0.36 divided by 5, 0.48 divided by 5, 0.096 minus 0.072 minus 0.096. I just divided the whole thing by 5, okay? 0.096, 0.128 minus 0.096 minus 0.128 minus 0.072 minus 0.096, 0.072, 0.096 minus 0.096 minus 0.128, 0.096 and 0.128. And same thing, 1, 2, 5, 6, 1, 2, 5, 6. Now we're going to assemble the matrix. Please pay attention. K equal to K1 plus K2. And how big the matrix? This depend on number of total degree of freedoms. How many degree of freedoms you got? 1, 2, 3, 4, 5, 6. So we need 6 by 6 matrix. Depending on that, so we have, let's say A is constant. We can have a 6 by 6 matrix. 1, 2, 3, 4, 5, 6. And one, 2, 3, 4, 5, 6. All right. 1, 1. Go to K1. 1, 1. So I think that is 1, 2, 3, 4. 1, 2, 3, 4. So 1, 1. Row 1, column 1. So you have 0.33. So you have 0.33 plus row 1, column 1, 0.072. You get 0.405. Column 2, row 1. So first you go to here. Column 2, row 1, 0. So that is fine. Column 2, row 1, 0.096. So 0.096. Column 3, row 1. There is no, there is a column 3, row 1, 0 minus 0.33. There is no column 3 that take it 0. So you can have minus 0.33. Column 4, row 1. There is a column 4, row 1, 0. And there is no column 4, so that is 0. So that is 0. Column 5, row 1. There is no column 5. Column 5, row 1, minus 0.36. Oh, here, minus 0.072. Minus 0.072. Column 6, row 1. There is no column 6, by the way, here. So then you have minus 0.096. Right. Similarly, so let's write 0.405. Similarly, column 1, row 2. Column 1, row 2, 0. Column 1, row 2, 0.096. 2, 2. Column 2, row 2. I hope you get the drill. 0.128. And there is a 0. So 0.128. Column 3, row 2. Column 3, here column 3, row 2, 0. And okay, let me. All right, so where are we now? So I hope you get the drill. 3, 2. Happening here. Okay. Got it. Thanks. Okay. All good. So far, so good. 3, 2. There is no 3 here. 3, 2, 0 and 4 to 0 as well. There is no 3, 2 here. So both are 0. 3 to 0, 4 to 0. 5 2. Only 5 2 is here. 6 2 is here. Minus 0.096 and minus 0.128. 3 1. Go here. 3 1 minus minus 43. 3 1. 3 2 0. 3 2 0. I hope you got it. Now I will just do it 0.333 0 0 0. So that is 3. 3. Now let's do the 4. 0 0 0 0 0 0 4. 5 6. Minus 0.072. Minus 0.096. 0 0. 0.072. 0.096. Minus 0.096. Minus 0.128. 0 0. 0.096. 0.128. Check, check. All diagonals are positive. Bang, all positive. This line, same, same. This line, same. This line, same. This, same. This, same. Perfect. Okay. So this is how you're going to do it. Unmute yourself. Anything you don't understand, put it in the chat if you don't understand anything of that things. I turn on my camera. So how did you arrange number of rows and columns? Which one? The capital K or K1 to K2? This one, small, this K1, K2 or this K? Sayyid Sah. How did you arrange number of rows and columns? 1, 2, 3, 4, 5, 6, because there are 6 degrees of freedoms. So what I put, there are 1, 2, 3, 4, 5, 6 total. You can see 1, 2, 3, 4 total 6 degrees of freedoms. So how do I arrange? Total 6 degrees of freedoms. So I make it 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And then what I do, I go column 1, row 1, and then I go to K1 and find out what is row 1 and column 1 number. And similarly, I go here and find out what is row 1 and column 1 number, and I add them together. Then I go here, column 2, row 1. And then I go here, column 2, row 1, and then come back here, column 2, row 1, and I find these details here and I add them together. Sayed Shah, is this we have to add only? We have different square area, A1 and A2. Maybe we need to calculate area and Young modulus earlier. All good. Okay, Narayan, I will help you at that one as well. So if you have different area, what you can do it? We can multiply this K1 and I will do it with Excel. What you do in here, you can just keep E out and multiply the whole thing by area. And then similarly, what you do, you cancel this E, you get the another 4 by 4 multiply by the area, and then you add them together. Narayan, is it possible? If you have different area, A1 and A2? Yes, it is possible for you. Just keep the constant, whatever, if the different E, you multiply everything, A and E, and you get K1 and K2 separate, and then you add them together in the capital K. Narayan Muhammad. All right. I don't want you to just You have undergraduate degree. You are an engineer. I don't want to teach you the maths. I'm not here to teach you the matrix. I'm not here to teach you to do these all nitty gritty things. Of course, it is a good skills. Of course, you need to have concentrations, but we need to use Excel. We need to making sure that I don't want to just blindly follow that one. So for that case, let's do the Excels. If you want to follow with me, we have another 20 minutes. I might go a bit quick, but we want to do the Excels. If you want, open the Excel, please. Let's do the Excel. So whatever the answers which I am giving you here, it is possible by Excel because it is a computer friendly methods. So how many nodes we got? So let's write this node here. Press light the node here and we put this. If you want to follow, just open the Excels, write the node. How many node we got? Oh, let's get the figure by the way. These ones. Copy. Let's get it here. So we know what we are talking about. So here you go. I hope you can see this Excel file. How many node we got? Circle, node number 1, node number 2, node number 3. So there are 3 nodes, 1, 2, and 3. If you want to center them, then just center them here. Anyone following with me? I can slow down. Or you just want to watch setbacks? You want to follow, say it. Okay, open it please, quick. We don't have much times to cover the whole things. All right, write down nodes and put the 1, 2, and 3. Second, we can put the X coordinate and Y coordinate of your node. Let's put the X meter, Y meter, and we go back to our questions here where we put the coordinate system. Where is it? Oh, here you go. So node number 1, you have 3 and 4 coordinate. X has a 3, Y has a 4. So you agree with me that for node number 1, I can put 3, I can put 4. Node number 2, you with me that node number 2 is here and it is 0, 0. Node number 2, it is 0, 0. And you can see from this figure as well that this is your starting point 0, 0. This is 3, this is 3 and this is 4. So this is 3, 4 and this node number 3 is 3 and 0. So 3 and 0, X and Y. This is X and Y coordinate. I just put it this way here. This number 3, 3 and 0, X and Y. OK, unmute yourself if you or put it in the chat if any of this one is not making sense. X and Y node numbering. Right, so far so good. What Syed X30? What do you mean? Do you have a question, Syed? X30. Yes, because node number 3. We have 0, 0 here. We go across by 3, no Y. So we have 3 and 0. Right, because you can look at this node number 3, node number 3. And we have explained you already this one 3, 0, node number 3, node number 3, 3, 0. All good, perfect. OK, let's move on. Anyone fall behind? Just yell out or put it in the chat. Let's put elements. And how many elements we got? 1 and 2. Look at this square bracket 1 and 2. Element 1 and 2. Area of the element number 1, let's say meter square. Area of the element number 1, let's say 0.006. I think it's given in our examples. And 0.002. Okay, so that is given in our examples, I think somewhere. Yep, it is given. It is not given. It's supposed to be given. Here you go. Area of the one 0.006. It is I think 0006. Please make a corrections. I think they are all here and everywhere. So make it 0.0006 and here 0.002. Just make a corrections. I will make a corrections in a minute. So 0.0006 and 0.002. So that's area of element number 1, 0.0006, 0.002, area of the element 1 and element 2 given in our examples. Young modulus is given in gigapascal. So I need to explain you that gigapascal story. So how much it is? It is 200 gigapascals. So if it is 200 gigapascals, we have this one in kilonewtons and we need in the meter. So we don't understand this gigapascals thing. So you can have giga meaning 10 to the power 9 pascals. I hope you understand. Giga, I put it 10 to the power 9. 200 times 10 to the power 9, 1 pascals, I can write kilonewton per meter square. Right, so I can see that I think this is I wanted. Oh, sorry, this one I can make it pascals meaning Newton per meter square. But I need in kilonewtons, so I can divide by thousands to get it in kilonewtons. So 200 times 10 to the power 6 kilonewton per meter square. So 200 gigapascals is equal to 200 times 10 to the power 6 kilonewton per meter square. Exactly the same, just the unit conversion. So I can put both Young modulus are same. So I can put Young modulus in kilonewton per meter square. And I can put equal to 200 times 10 to the power 6. And I can just scroll it down. So 200 times 10 to the power 6, and I just scroll it down. All right, then after we're going to put the length of element number 1 in the meter. No question so far, so should be fine. Everything is smooth. So length of these guys here is length of these guys here 3 meters. First one, element number 1, and this one we calculated 5 meters. You remember that, right? 3 meters and 5 meters. So here it is given 3 meters and we calculated this 5 meters, I think from Pythagoras theorem. So that is all good. Length is given. Now we can calculate lambda x. If you want to get the lambda x, you can go insert symbol. If I can find that symbol, lambda, you can get it somewhere, maybe. If you don't get it, you can put any, just put x, or you can put lambda, or I can put lambda x. That is not an important. OK, here I got the lambda, or you can just put lambda x, or you can put just like this lambda x like this. So that's still fine. OK, it's not a big issue. That is not a part of our story. So you remember lambda x for element number 1, how we calculated? That is, you remember xf 3 minus 0 over 5, right? So that is your where is it? Lambda x here. So 3 minus 0 over 3. How did we calculate it? that is 3 and 4. So that's 3 minus 0 over 3. That's we calculated. So I can show it to you. Equal to bracket. And this is here. So 3. So node number 3. Node number 3x minus node number 2x. Node number 2x divided by the length. Right? I can stop here. This is the element number 1, and x of this 3 minus x of 2. This is far node, near node. So that's what we done. I think we already done 3 minus 0 over length 3. Enter. 1. You can see in our calculation it was 1. Similarly, you have y of this one, take away y of 3, take away y of 2. So bracket y of 3, take away y of 2 divided by length. So you get 1 and 0. Right. Similarly, you can just get it here. Insert symbol. We already got this. We got this lambda y and lambda y. And similarly, you remember this story here. That element number 1, you have this 0, 0 over 3. Oh, sorry. This is, I think I done it wrong here. This was supposed to be here. Control X. Sorry, just make it correction here. I think bracket. This is Y. So this one, take away this because this is element number 1. So please make a corrections. Take away this one divided by length held. Right. So this is element number 1. I was just putting that value in element number 2. Now, element number 2, we have here, this is 0, 0, and this one is 3 and 4. So x of this number 1, bracket, x of number 1, take away x of number 2, divided by length, 0.6. I think if you check our calculation, it is 0.6. Bracket, y of this number 1, take away y of this number 2, y of this number 2, divided by length L. So that is 0.8. So if you check this lambda x and lambda y value, you will find the exactly the same 0.6 and 0.8. So it's following. Now, if you want, you can just find out AE over L. So area times by Young modulus divided by length, making sure all units are same. Meter square, kilonewton meter square, meters, not in any other ones, and you can just scroll it down like this. If you want to calculate just 1 over L, you can do that. You can have equal to 1 divided by L. And you can just click on here, and when you get this corner, you can just scroll it down. Right. All good so far? Now the magic will start from here. Magic will start from here, meaning this is the fun part. So let's say we have, we can put element 1, and let's put this value K1 here. Let's say capital K1. What was the equations, by the way? Let's get that equations from here. Where is that equations? Oh, here you go. Let's put that equations. Copy. Yep, I'm coming. Control V. All right, what is the questions there? Rashid Muhammad. Why 1 over L? If you don't want, I will explain you when we needed why 1 over 1. Okay, 1 over L. So that's, I will explain you why 1 over L. Just leave it there. Just fit with that ones. Sometimes don't use those short notice, and probably sometimes I may not be able to recognize, but this time I done it. So good. Okay, so now here we can have a, let's put our lambda x. So let's put this one in the some colors. Let's put some colors. Let's put one color here, and we need 4 by 4. So just highlight 4 by 4 and let's make some lighter color here. Something like that. OK. And probably you want to use this kind of a border. And probably want this kind of a border. OK. Probably use this some kind of a lighter color. So that would be different. OK. So let's say K1. Yeah, let's make it center. So lambda x square. Watch it here. Equal to lambda x square. I think I just made it 3 by 3. How about we make it one more? OK, 4 by 4 equal to this one, lambda x times lambda y. Lambda x times lambda y. Please note element number 1. OK, 0 equal to minus. Please be careful here. Use the bracket. If I don't use the bracket and if I do it this one, it will just give me the positive answers, and which is not correct. Please make sure you use the bracket before this and these ones. Then it will give you the correct answer -1, because this minus is not, you need to minus it square. This minus is separate. So therefore you need to make sure that you done this equal to minus lambda x times lambda y. Very good. OK, so this is all done so far. Similarly, lambda x times lambda y. Lambda x times lambda y. Lambda y square is equal to lambda y square is equal to minus lambda x times lambda y is equal to, be careful here, minus bracket lambda y square. All right. And then you can minus lambda x square. So equal to minus lambda x square bracket. Please use the bracket. Why it's not coming up minus, please? Come on. Oh, because I put the bracket before, so square and then bracket like this. Perfect. And then you have minus lambda x times lambda y equal to lambda x square. And here equal to lambda x times lambda y. Perfect. And then equal to minus lambda x times lambda y. equal to minus bracket lambda y, not bracket over, square, and then bracket over. And then lambda x, lambda y equal to lambda x times lambda y. And then you can have it equal to lambda y square. Oh, sorry. Lambda y square. All right, so yeah, look at this. These diagonals is positive. This number 0, minus 1, 0. Perfect. 0, 0 here. This one, these guys are same as this ones. OK, checking is done. All very good. All right, now if you want to check with your answers, you can do the check. 1, minus 1, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0, 0. That's perfect. Now, if you want to divide by 1 over L, what you can do it? Oh, by the way, you can put 1, 2, 3, 4. 1, 2, because that is the degree of freedoms. You remember that 1, 2, 3, 4. And similarly, you can do 1, 2, 3, and 4. Right. So let's put it in the different colors. 1, 2, 3, 4. And let's put this one here. 1, 2, 3, 4. Right. You can do several things here. If I just copy this one, copy and Control V, and let's put it in the different colors. Let's say these colors, and let's put these colors here. If you want to divide this whole thing by 1 over L, because you remember that we divide by 1 over L. So let's cancel this. These numbers divided by, let's say, length, and we need to lock it. How do you lock it? You can put the $sign here and $sign here. So it will not gonna change. So you can just watch it. You can go across and you can scroll it down. So you get the whole matrix that is AE 1 over L. If you want to multiply AE or these whole things, you can do that. I can show it to you. Control C, Control V. So let's say you want to multiply AE over L. So multiply AE over L, and we want to lock it. Lock it means we don't want to change. $3, and then you can just, so when you do these ones, look, they don't change. See, K9 change because here you have J9, K9 become that, but that lock person did not change. So we can just go across and here. So that is your K1s, whatever you want to do it. I think we are very close to finishing, but stay back for 5 minutes. We are going to finish soon. Now, look at the magic here. That's the beauty of one. So if I want to do these ones, and I think we need to make it 6 by 6 matrix. So let me make it 6 by 6 matrix now, because we need 6 by 6 matrix at the end. So let's do this. Control C, Control V, and let's make a different color here. Different colors meaning let's make it yellow and here. So here we will have a 5 and 6 because we need 6 by 6 matrix. And let's use the same format of these guys here. So here we're going to have this matrix 1. And then we just going to scroll it here. No, up to 4. Okay, that's anyway. So we're going to do it 1, 2, 3, 4, and then these 4s, and all others are going to be empty. And this one would be empty. So you have 4 by 4 matrix in the format of 2, 3, 4. I know it is a little bit overwhelming, but I think if you do it by yourself, and we will do it more practice on this one, probably that will be more kind of useful. All right, so that's all good. We make a 6 by 6 matrix with 4 by 4. Let me put this one in the red colors with these ones. Okay. So this is all good. Now element number 2 is quite simple. What we do it, we just copy this whole things and we paste it here. Control V. Right. So look at these ones. If you look at this element number 2, oh, sorry, Control Z. If you look at this element number 2 here, we can just click on here and we can find that these numbers is not right because lambda x is here. For element number 1, we can just, what we do, we click on here, and when we get these ones, we do move it here, lambda x squares. You can see that magic. You can double click on here, and then you move this for element number 2 to element number 2. And if you want, you can move this one to here. Here, you can move these two. In here, you can move these two guys here. In here, you can move these two. In here, you can move this one. In here, these two need to be, oh, sorry. These two need to be go here. These two need to be go here. Similarly, we can move this one here. This one move here. Just the last bit, please. And then you can move this one here. Here we will have this one. Oh, sorry. And this one goes here. There you go. Okay, so if you look at this matrix, probably this one is not correct. We need to move this one here. Okay, again check diagonal positive. This number same as these numbers. These numbers. Oh, this one not same. What happens here? Probably we did not change these ones. Oh, yep, here you can see. So you can easily catch that. So this one goes here. This one goes here. Oh, sorry. And this one, oh, sorry. It is sometimes my mouse is not working. Let me. It is sometimes easy to do this way. Okay, that is better. And then if you just want to move this guy here, I think this is better. So now you don't need to do anything here because look at this. This is already done for you. Make sure this length is changing here. And then bang, you can just do this. And these numbers are changing automatically. Look at that. OK, here you want to change it to this one. And these ones, and there you go. And here you want to have it, I think we have another degree of freedoms, which is 1, 2, 5, 6, I believe. Here 1, 2, 5, 6. So in here you need to make it 1, 2, 5, 6. 1, 2, 5, 6. 5, 6. And let me copy this. Control V. Control V. And 1, 2, 5, 6. Now in here, we need to be careful with this matrix because you have 1, 2 is correct, but this is not correct. 3, 4 and 3, 4 is not correct because we need to make it 5, 6. So 5, 6 and this way. OK, this one 5 and 5. So 5 and 5 is here. So 5 and 5 here. So we get 5 and 5. And here. It requires a bit of practice, but anyway, we can do it together. Sometimes next week, 1 and 5. So, and then you can do it down. And now what we need to assemble that. Control C, Control V. And what we do it, we add this number by these numbers. You remember 1 plus 1, do you remember that, right? And the beauty of these ones, we can do it very easily here, like this, and bang. You can have these numbers exactly the same, diagonal positive. This number 0, 0, 0, this number same, this number same, this number same. Let's confirm that these are same. So this is how the process works. You can assemble all these and you can compare your answers with your hand calculations and so on.